Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing BGP, concepts, configuration, and monitoring in Junos. In this lesson, we'll be covering the configuration and monitoring of internal and external BGP, along with the policies to influence BGP route advertisements. As we covered in a previous lesson, iBGP and eBGP peers have different loop prevention rules. iBGP will re-advertise any routes learned from eBGP peers, though it will not re-advertise routes learned from other iBGP peers. eBGP, however, will advertise any routes in the BGP protocol to an eBGP peer by default. In this lesson, we'll learn how to configure an iBGP peer, an eBGP peer, and how to influence the route advertisements by the application of export policies. So, let's get started by first reviewing our topology and the details of the configuration goals. The configuration and monitoring example that we'll be doing today will be in the context of this topology here. We have the Enterprise Autonomous System at the bottom. The Enterprise connects to two Internet Service Providers, ISP-A and ISP-B. Our Enterprise is running iBGP internally, as we see here between R1 and R2, and we're peering with our ISPs using eBGP. During this lesson, we'll be performing these three configuration steps. We'll first configure BGP. We need to configure an iBGP session between the loopback addresses of R1 and R2, and an eBGP session between the interface IP addresses. Next, we'll configure the next hop self policy so that iBGP peers within our enterprise can use the routes learned over eBGP from our edge routers R1 and R2. Finally, we'll review how to configure an aggregate route and show how to configure a routing policy to distribute the aggregate route into BGP. So, let's get started with reviewing example configuration for iBGP and eBGP peers. Here, we have the sample BGP configuration on the left. We have two BGP groups configured, the ISP-A group and the Enterprise group. The ISP-A group has the type command configured, setting the group as type external. Another valid option for the type is internal. If the internal type is used, the peer AS command is not needed, since the AS is then known to be the same as the local router's AS. The local router's AS must be defined for BGP to operate. It may be configured either in the routing options hierarchy, as it is here using the autonomous system command, or in the BGP protocol hierarchy. In the BGP protocol hierarchy, the local router's AS is configured with the local AS command. Finally, something to note about the BGP neighbor configuration is that many BGP configurations, like the session type and import and export policies, may be configured at different hierarchies. They may be configured at the neighbor level, at the group level, or at the protocol level. If multiple conflicting configurations are present, then the configuration applied to the most specific hierarchy will take precedence. This means that a configuration at the neighbor level will take precedence over a conflicting configuration at the group level, and the group level will take precedence over the protocol level. Let's now move on to configuring an export policy you're likely to see in practice, a next hop self policy. As we've mentioned in a previous lesson, routes learned over an eBGP peering session and re-advertised to iBGP peers will have a next hop of the interface IP address of the eBGP peer. Unless that interface on your enterprise's edge router participates in your IGP, then the next hop will be unreachable by the other routers in your network. This can be resolved by setting an export policy on your edge router, on the group or neighbors that are IBGP peers, to change the next hop of advertised routes to IBGP peers to be its IBGP peering address. This address is typically the loopback address, as it is best practice to peer IBGP between loopbacks. As we see in the configuration snippet below, we have the policy configuration on the right. This policy is named NextHop Self, though could be named anything. The term is BGP term. This policy matches routes from the BGP protocol table, which are eBGP learned routes. The action taken on these routes is below in the then action, where we're setting the next hop to self. Note that we're not using the accept action, only the next hop action. On the left, we see how this policy is then applied in the BGP protocol configuration hierarchy. Within the enterprise BGP group, we've applied this policy as an export policy, so that routes being advertised to other IBGP peers will have the policy applied. Great. Next, let's configure another policy for use in our BGP configuration, an aggregate route policy. Many times, an enterprise will have a need to advertise a summary route. This may be used to influence traffic patterns, such that peers advertising more specific routes are preferred over those advertising the aggregate or summary prefixes. This could also be done simply as best practice to limit the size of the global internet IPv4 routing table. In order to advertise an aggregate route into BGP, the route must be present in the local device's routing table. So, we need to configure an aggregate route first. In this configuration snippet, on the right, we first have our aggregate route configuration on top. We've configured the 172.16.0.0/21 aggregate route. Now, by default, only BGP routes will be advertised to BGP peers. So, we need to configure an export policy to inject our aggregate into BGP. Below, we have our policy configuration. This BGP aggregate policy matches routes in the aggregate protocol and uses a route filter to match this exact 172.16/21 prefix. Here, we're not modifying any attributes about the route. We're simply accepting it. In our BGP configuration on the left, we see that the policy is applied at our ISPA group level as an export policy, allowing us to advertise the 172.16/21 route to ISPA. And since the peering is an eBGP peering session, the next hop, by default, will be the interface IP address connected to the ISPA router. Excellent. Now let's move on to monitoring BGP. First, we'll review our peering sessions. Using the show BGP summary command, we can see a list of our configured BGP neighbors and their current state. The top output is from R1, shown here in the diagram, and the bottom from R2, shown here. As expected, R2 only has a single neighbor, and R1 has two neighbors. From the left, we have the IP address of the peer. This is the configured neighbor IP in the BGP configuration of the local device. We then have the AS of the peer. The following three columns are statistics information on the number of BGP packets received from the peer, number sent to the peer, and the queue of BGP updates yet to be sent to the peer. The following column shows the number of times the local device has seen this peering session flap. The following column shows the amount of time since the last state transition has occurred. As you may recall from another lesson, the BGP state machine has several states between idle and established. This flap and timer values are only concerned with a peer being in established state or not. Finally, the last column is a multi-purpose column. In the case that a peering session is not yet established, this column shows the state of the session. If it is established, it will show the number of received route advertisements which are active, received, accepted, and dampened. There are two sets of this statistical information here, as the left set displays the inet.0 IPv4 unicast table, and the set on the right shows the inet.2 IPv4 multicast table information. In the next slide, we'll take a closer look at the details for a particular BGP neighbor. Using the show BGP neighbor command, we can see the details of all configured neighbors. We can append the peer IP address of a particular neighbor to this command to see the operational details of a specific neighbor as well. This output includes a lot of information that can be helpful for validating the current operation of a BGP peer. We see the type of BGP session, state of the session, and whether any export policies are in place which affect this peer. We also have the options available for this peer, and some other useful information below not seen in the summary output, like the hold time and keep alive interval, and the status of BFD. Although it's not covered in detail in the JNCIS ENT, BFD is bidirectional forwarding detection. It is a protocol which can allow for much faster detection of communication failure than many routing protocols' built-in mechanisms. Finally, let's review the commands used to validate the routing information being advertised and received to and from a BGP neighbor. First, we'll review the routes received from a BGP peer. Using the show route receive protocol command, we can review the BGP routes received from a particular BGP peer by supplying the peer IP. As we see in this output, R1 is only receiving a default route from ISP-A, and R2 is seeing that default route received from R1. Notice that the AS path is included with a BGP route on the right. The converse to the receive protocol command is the show route advertising protocol command. Using this, we can review the routes which are being advertised to a particular BGP peer. This output will include routes advertised due to some export policy as well. We see from R1 that we're advertising the default route to R2. I appreciate you sticking with me to review configuration and monitoring tasks with BGP. I hope that this lesson has been informative for you, and I would like to thank you for viewing.